Welcome to The Explainer. Today, we're on a highly energetic mission to demystify the invisible digital brains that are literally running our modern world. I mean, from the cars we drive every day to the life-saving medical devices in hospitals, embedded systems are silently calling the shots behind the scenes. But how exactly do they pull this off without failing when it matters most? Well, let's find out. So think about this for a second. What do a failing jet engine and a glitchy microwave actually have in common? On the surface, absolutely nothing, right? But underneath, both rely on embedded systems to process information and execute commands. The real difference, though, lies in the life or death stakes of their timing. A 1-second delay in your microwave? Well, your soup is just slightly less warm. A 1-second delay in a jet engine's control unit? Yeah, that's a completely different story. Okay, let's dive into the system tolerance matrix. This really perfectly illustrates the divide between hard and soft real-time systems. In hard real-time systems, think flight management or your car's anti-lock brakes, missing a deadline is strictly not an option. There is zero margin for error here, and computed values are entirely useless if they arrive even a fraction of a millisecond late. Failure here equals catastrophe, plain and simple. On the flip side, we have soft real-time systems, like MP3 players or climate controls. The deadline tolerance here is way more flexible. A late data packet might cause a degraded user experience, maybe a temporary glitch, but it still has some functional value. No one is in actual danger. So here is our roadmap for today. We'll be looking at 1. The stakes of real-time systems, 2. The legacy superloop architecture, 3. Escaping the non-determinism trap, 4. The brilliant multitasking illusion, 5. The real-time OS ecosystem, and finally 6. The ultimate architecture showdown. Moving right along to Section 2, the legacy superloop architecture. So, in legacy foreground/background systems, which engineers often call superloops, the setup is wonderfully simple but honestly highly constrained. The application is basically just one giant infinite loop running continuously in the background. It just cycles through calling different modules to perform operations. But what happens when an event needs immediate attention? That's where the foreground comes in, handled by asynchronous interrupt service routines, or ISRs. When a button is pressed or a sensor triggers, the ISR fires like a lightning bolt, immediately interrupting that background loop. This is the standard for simpler things like microwaves and toys, and, it works perfectly until your system complexity starts to scale up. Section 3. Escaping the non-determinism trap. So what actually happens to our system when a critical background task is repeatedly interrupted and delayed by this basic bloated loop structure? What's really interesting here is pinpointing the exact moment this legacy architecture falls apart. Imagine an ISR is triggered by a sensor, but the data it provides just sits there, completely unprocessed. Why? Because the system physically has to wait until the background loop rotates all the way back around to the relevant module. And because the time it takes to execute the code varies with every single loop pass, the response time becomes totally unpredictable. In engineering, we call this unpredictability non-determinism. And in a hard real-time system, non-determinism is a trap that can absolutely lead to catastrophic failure. And the danger isn't just about time either. It's about data integrity. We need to define two major concepts here. First up, a critical section. This is a piece of code that must be treated indivisibly, meaning once it starts executing, it absolutely must not be interrupted. Second, we have shared resources. This could be an I/O device like a display, or just a variable in memory that's being used by multiple tasks. To prevent data corruption, a task must gain exclusive access to that shared resource, which is a process called mutual exclusion. If our legacy superloop fails to manage this timing perfectly, your data just gets completely scrambled. Section 4. The brilliant multitasking illusion. The solution to all this chaos starts by breaking that massive, unpredictable superloop into smaller, bite-sized, manageable pieces called tasks or threads. Now, a task is simply a small program, but here is the absolute genius part. The task is designed to think it has the central processing unit completely to itself. It operates in total blissful ignorance of anything else happening on the chip. In reality, on a single CPU, only one task can execute at any given exact moment. So the system rapidly shifts the CPU's attention back and forth between these sequential tasks. This modularity makes complex code vastly easier for engineers to design and maintain. And this brings up a fascinating duality within the system. From the task's perspective, there's this grand illusion of CPU ownership. The task assumes it has exclusive, uninterrupted access to execute its code. But in the kernel's reality, right behind the curtain, a piece of software called the scheduler is working frantically. It's executing rapid context switches, stopping one task, saving its exact place, and starting another based on strict priority levels. It's time slicing so incredibly fast that it creates the illusion of multiple CPUs working simultaneously. It's really like digital magic. To manage this crazy juggling act, every task exists within a very rigid state machine. From the programmer's perspective, a task is always in one of 5 basic states. It starts out dormant, just residing quietly in memory. Once it's created, it becomes ready, waiting in line for its turn. When the scheduler picks it, it is running, officially owning the CPU. But it can be interrupted at any moment by a hardware event. Or, and this is cool, it can voluntarily step down into a pending state if it hits a blocking call, like waiting for a shared resource to free up. During that pending state, it uses absolutely 0 CPU time, which keeps the whole system incredibly efficient. Moving to Section 5, the real-time OS ecosystem. So zooming out to look at the broader system stack reveals a really fundamental distinction you need to understand. Down at the very center, you have the raw hardware. Wrapping right around that is Layer 2, the real-time kernel. Now, the kernel is strictly responsible for scheduling and time management. It manages the CPU itself. But moving out to Layer 3, we have the broader RTOS ecosystem. The golden rule to remember here is this. A kernel manages the CPU, while an RTOS manages the entire system. Let's look a bit closer at that core manager, the real-time kernel. You might actually think that managing all this time, memory, and hardware resources would just severely bog down the processor. But a real-time kernel is remarkably efficient. In a well-designed application, it consumes only 2 to 4% of a CPU's time. Think about that. It requires a tiny footprint, sometimes just 1 kilobyte of RAM, yet it provides roughly 70 indispensable system services to keep everything running flawlessly. It is unbelievably lean. And building on top of that ultra-lean kernel is the RTOS constellation. You see, an RTOS isn't just one giant monolithic block of code that you're forced to swallow whole. It is a highly customizable suite. You've got your central real-time kernel, and you only plug in the independent components you actually require for your specific application. Need a graphical user interface? Boom, plug it in. Need a file system or a USB stack? Add it. You only use, and pay for in terms of processing power, exactly what you need. And finally, Section 6, the ultimate architecture showdown. So, the absolutely crucial takeaway today is the contrast between these two approaches. The legacy foreground/background system relies on a bloated, infinite superloop where event handling happens entirely inside interrupts. This leads to highly unpredictable, non-deterministic response times. It's great for low-cost, simple consumer goods, for sure, but the preemptive real-time kernel, that gives us prioritized multitasking. ISRs are kept incredibly lean. They just signal high-priority tasks to take over. This guarantees an immediate context switch and a deterministic response time. It is without a doubt the absolute gold standard for complex, critical, and scalable embedded applications. Which leaves us with this final thought for our explainer today. We've seen exactly how real-time operating systems conjure this brilliant illusion of simultaneous execution to keep our world running safely. But when a missed deadline equals a true catastrophe, can we ever afford an illusion of control that isn't perfectly, flawlessly timed? The invisible digital brains around us are working literal miracles in fractions of a millisecond. I really hope this look into their architecture has made you appreciate that hidden precision and leaves you eager to uncover even more about the incredible systems powering our everyday lives.